Ladies and gentlemen, good afternoon. I have to say I'm very excited and honored to come to London and attend such a wonderful conference. And today, the topic I want to share is a confinement model for concrete-filled circular tubes. My presentation covers the four main parts. First, I will briefly introduce the background of this research work. Then I will present some study results on the stress analysis of the steel tubes of for the concrete-filled tubes. Third, I will discuss the equivalent confining stresses. Last, I would like to give some concluding remarks. This study is focused on the concrete-filled tubes, where the axial loads are applied to the concrete cores directly, while the encasing steel tubes provide confinement to the concrete cores. As shown in this figure, the steel tube is deliberately made slightly shorter than the concrete core to avoid carrying direct axial loads. And in practice, the steel tube is generally disconnected at the beam-to-column joints. Thus, to enhance the stiffness and the bending stress of this kind of column, the concrete core always needs to be reinforced by steel bars or steel sheets, as shown in these two figures. This kind of composition construction possesses many advantages. First, I think there's no local buckling of the steel tube, and the stress of the thin-walled, high-stress steel tube can be fully utilized. Another advantage is the excellent seismic the column performed due to the effective confinement, even when high-stress concrete is used. The third advantage is good fail-resistant performance. That is because the load-carrying steels, like steel bars or steel sheets, are embedded in the concrete and protected by the concrete. The last important advantage is the ease for construction. On one hand, the steel tube can be used as a formwork for concrete pouring during the construction. And on the other hand, due to the disconnection of the steel tube, the construction of the beam-to-column joints is simplified, especially when connected with RC beams. In recent years, due to the superior structural behavior, the concrete-filled tubes have been used in construction for nearly 20 projects in China, including high-rise buildings and large-span structures. And they have gained good economical benefits. The investigations on the basic structural behavior of concrete-filled tubes can date back to 1967. Professor Gardner et al. Conducted a test to investigate the influence of unloading condition on the traditional CFSTs. And their study included the special CFSTs where the only concrete core is loaded. In their study, the end loading condition has little influence on the axial resistance of CFST columns due to large friction between the concrete cores and the steel tubes. To further enhance the confinement, Orito et al. Focus on the concrete-filled steel tubes with greases. That is the unbonding steel tube concrete. This kind of column have a better confinement and higher axial resistance than traditional CFST, but with reduced axial stiffnesses. In 1985, Tommy firstly investigated the behavior of reinforced concrete columns with circular shear links. In their study, the steel tubes are considered as an extreme situation of using traditional hoops of shear links with a zero spacing, and they are fully utilized for confinement. Due to the special unloading condition, the load carrying and the confinement mechanism of this kind of column are still deserving to be investigated. As shown in this figure, as the column ends, slip between the steel tube and concrete may occur along the column head. But with the accumulation of the frictional stress, the slip may be overcome, and the steel tube as mid-head region may deform accordingly with the concrete core. Therefore, the tube stresses vary in each section along the column head. Here I list 3 key issues to be investigated. The distribution of the tube stresses along the column head, the influence of longitudinal tube stress on the axial resistance of the concrete cores, and the determination of the effective confining stresses. And all these issues are related to the confinement model in this study. To investigate the confinement, we first focus on the stress state of the steel tube. As shown in this figure, for simplification, the steel tube is theoretically divided into 2 regions. One is the slip region at the column ends, and the other one is the non-slip region at the mid-head. In the slip region, frictional stress accumulates along the column head, while in the non-slip region, the friction stress is assumed to be gone. And based on the division, we can get 2 characteristic sections, end section and boundary section. For the end sections, there is no longitudinal strain, and the transverse strain of the steel tube is equal to that of the concrete. While in the boundary section, both the longitudinal and the transverse strains are equal to those of the concrete. Based on the strain relationship, we developed a calculating program for predicting the stress development in the end section and the boundary section. Here is a comparison between the predicted results and the test results. As shown in these 2 figures, they are in a good agreement. Besides, for the end sections, the steel tubes yield transversely at the peak loads, while for the boundary section, the transverse stress increase at a later loading stage, and they cannot reach the yield strength. Next, let's discuss the distribution of tube stresses along the column head at peak loads. In this analysis, 2 basic assumptions were adopted. First, the friction in the steel to concrete interface is proportional to the confining pressure. Second, the steel tube is assumed to be under the plane plastic stress condition. Both of these assumptions were verified by the test results. And based on this, we can take out a micro unit of the steel tube in the slip region to analyze the tube stresses. In the longitudinal direction, we can establish the equilibrium equation and then combine it with the Formas's yield criteria. And based on this, we can derive the parametric equations for predicting the tube stresses at the peak loads. This figure shows the relationship between the tube stress and the variable HC. HC can be calculated by mu 2D and multiply H, where mu is the frictional factor between the steel tube and the concrete. D is diameter of the steel tube, and H is the distance between the starting section to the end section. As shown in this figure, the longitudinal stress increases with the variable HC, while the transverse stress decreases with the variable AC. These results are in accord with our conceptual analysis. However, the parametric equations are derived within the slip region. And that is to say, in this figure, the curves beyond the boundary section are meaningless. So it is necessary to determine the location of the boundary section. That is the height of the slip region. Based on the existing test results, we found that the variable HC as the peak load moment turns to be a constant value of 0.4. And knowing that, we can take out the effective path of the stress curves. As shown in this figure, an approximately linear relationship was found. And from this analysis, the linear simplified equations to predict the tube stresses were proposed. And this figure shows the distribution of the tube stresses at the peak load moment. The tube stresses in the slip region vary in each section linearly along the column height, while they keep constant in the non-slip region. The height of the slip region to the diameter of the tube ratio is approximately equal to 0.4 to mu. Knowing the distribution of tube stresses, next let's discuss the simplification for the confining stress. As we know, the confinement effect is determined by the transverse stress. So in this analysis for simplification, the average transverse stress along the column height was adopted to estimate the tube confinement, as shown in these figures. And in the calculation, a reduction factor for the transverse stress KH is induced to consider the effect of the column height and the frictional factor between the steel tube and the concrete. To verify the rationality, the proposed equivalent confining stresses were applied to four classic confined concrete stress model. And for all these models, the predicted results were in a good agreement with the test results, which verifies the rationality of the proposed confinement model. Based on this study, I would like to give some concluding remarks. First, the longitudinal stresses of the steel tubes should not be considered, since the failure position is uncertain during different kind of loads. Second, to reduce the differences in stress resistance along the column height and to improve the economical benefits, thin-walled high-stress steel tubes are suggested to be used in concrete-filled circular tubes. Last, in seismic calculation, the equivalent confinement of steel tube in the column plastic hinge should be considered. Lastly, I would like to bring the warm greeting from China region. This is a group photo of Abstract E China Young Researchers Conference held last year in Chongqing University. And the China region has about 400 members, and it is administered by Architectural Design Institute of Shanghai, Tongji, yes, here, in Shanghai. That's all for my presentation, and I sincerely welcome you to come to Chongqing. That's all. Thank you.